Trig functions can be amongst the trickiest functions to integrate. Luckily, there are some pretty straightforward methods, especially when dealing with the products of trig functions. So when I'm looking for an even or odd function to integrate, I'm looking for a situation where the integrand looks like, and we'll start with just the sines and cosines. So I have a product of sine and cosine, and they're raised to some power. It's not required that the power be the same. If I want to differentiate this, or integrate this, I need to pull some tools out of my toolbox. So let's make a list of the tools I want to use. First, let's make use of the fact that sine and cosine are derivatives and integrals of each other. So if I were to want just the integral of sine x dx, well, that is the opposite of cos x plus c. And the integral or antiderivative of cos x dx is just sine x. Also, we have identities to work with. And when I'm dealing with sine and cosines, the most commonly used will be the Pythagorean identity, sine squared of x plus cos squared of x equals 1, and the power reducing formulas for sine squared and cos squared, starting with sine squared of x equals 1 minus cos 2x over 2, and the cos squared of x equals 1 plus the cos of 2x over 2. Sometimes better written 1/2 times 1 minus cos 2x and 1/2 times 1 minus cos, plus cos of 2x. So the trick here is to evaluate the nature of m and n. So if m or n, and this is or, n is odd and positive, we're going to use the Pythagorean identity. If m and n are even, then we'll use the two power reducing formulas. And remember, 0 is an even number. And you'll see in a minute how that plays. So let's do some examples, and it'll start to make sense what I've written here as we work through a few examples. Let's find the antiderivative of sine to the 4th of x times cos cubed of x. So I'm looking at a product of sine and cosine, and now I just want to evaluate what I'm dealing with. I either have m and n are even, that is not true because cos is an odd function, or I have m or n is odd. Oh, I have cosine of x is odd, and by the way, 3 is positive. So I'm going to use the Pythagorean trig identity. But the trouble is, the Pythagorean identity has cos squared and sine squared, but I'm looking at cos cubed. No worries, I can just rewrite this. Sine to the 4th of x times cos squared of x times cos x. All I did was expand cos cubed into cos squared times cos dx. Now, if I do a substitution on this, I can rewrite sine to the 4th of x times, well, cos squared is 1 take away sine squared, so 1 minus sine squared of x cos x dx. I'm going to do one more step, which is very anti-intuitive, and then I'll explain it after. I'm going to distribute the sine to the 4th. I'm actually going to do 2 more steps. So this would be sine 4th x minus sine to the 4th x sine squared x all times the cos x dx. And now I'm going to distribute cos x. So I have sine to the fourth x cos x dx minus, oh, I better not do that. Skipping a step. Not fair when you're learning something new. Minus, well, let's see, I've distributed cos x into the sine to the fourth x, and now I want to distribute it into this. But notice sine to the fourth, sine squared is just sine to the sixth x times the cos x that I distributed. Dx. All right, now I can separate them. This is the step I almost did just a second ago. Sine to the fourth x cos x dx minus the integral sine to the sixth x cos x dx. Now let's go back and reevaluate what I did here. So first things first, I noticed that I had the pattern n is odd and positive. So that's the substitution I'm going to make. I made a substitution, or first I separated so that I had a cos squared of x, so I could use the Pythagorean identity. And then I substituted sine squared, or 1 minus sine squared, into my cos squared. Then I did a whole bunch of distributions and like, what? This part takes practice just to recognize. But all I really did at this stage of the game was I distributed sine to the fourth in, right, ending up here. And then I distributed my cos x in, ending up with this line. And then I just use integration rules, which is when I have one integral subtracted, or one integrand, or an integrand with a subtraction in it, I can turn that to one integrand, or one integral minus the other integral. So that's all I've done at this stage of the game. But let's pause a second and see what we've done. Well, clearly in this case, we'll remember that if I were to let u equals sine x, then du equals cos x dx plus c, but for the sake of substitution, we don't tend to write that c in. Well, that's true here, but check it out. That's also true here. So I can actually substitute in each one directly. So I'm going to look for the integral of u to the fourth du, because cos x dx equals du, minus the integral of u to the sixth du. Well, those are just direct formula integration, which is just, in the first case, oh, we don't need an integration symbol anymore because we're actually integrating. That's u to the 4 plus 1 is 5, divided by 4 plus 1 is 5, minus u to the 6 plus 1 is 7 over 7, plus c. Now we have to throw in the plus c because I've done my integration. And now I'm just going to substitute directly back in. So I have sine to the fifth of x over 5 minus sine to the seventh of x over 7 plus c. And I am finished. All right, so that one was tricky enough. I think another example of the exact same case makes sense at this stage of the game. So this time we want to find the antiderivative of sine to the fifth of x times the square root of cos x dx. All right, so first case, we look at this, first instinct, panic a little bit. Okay, get that out of the way, take a deep breath, and let's just do what we know. Well, first off, we know we don't want to deal with this radical. So let's rewrite this as sine to the fifth of x times the cos 1/2 power of x dx. Okay, we don't like the fraction, much better than the radical, but it's definitely better because I'm looking at the form sine m cos n, sine m times cos n dx. What am I going to do? Well, m and n both even? No, that's not true. M or n is odd and positive. So in this case, I'm looking at using the Pythagorean identity. So I'm going to use sine squared of x equals 1 minus cos squared x. But I'm not dealing with a sine squared, right? Remember, we have to pull out one of the signs to make it even. So when I do that, I'm going to get sine to the fourth of x, and then I just remember the pattern, and you'll get to where you do remember the pattern, but I'm going to put the sine x back here, because when we pull one of the factors out of the odd powered function, we're actually setting up our du for the u substitution. So I'm going to go ahead and write it back here. It just saves me one step. In the beginning of working with these, you're likely to forget that and have to do an extra step. No big deal. That's all part of learning. But I'm going to go ahead and set it up. So here's what I have. Now, if I look, though, I'm wanting to substitute sine squared, but this is a sine fourth. That's okay, because sine to the fourth of x just equals sine squared of x squared, right? So that's 1 minus cos squared of x squared. So I can still do that substitution. So that means I'm looking at the integral of 1 minus cos squared x squared times the cos of 1/2 x sine x dx. So I know you're looking at your screen right now and thinking to yourself, Marla, that is not better. But trust me, it is better. With a little bit of practice, you'll start to see the pattern. It's always the same sort of cycle of events, and everything will come together for you. This is the part that probably has you just a little bit panicked at this stage of the game. You're looking at 1 minus cos squared of x squared. Well, what the heck is that? Well, let's do a simple substitution and see. If I were to turn this, let's just let cos x equal a. This would be 1 minus a. I'm sorry, let's let cos squared of x equal a. 1 minus a squared. But what is that? That's just 1 minus 2a plus a squared, right? It's just a simple binomial distributed or squared. So a binomial a minus b squared. So I have 1 minus, well, let's take the a out and put back in the cos squared of x. 1 minus 2 cos squared x plus cos squared squared cos to the fourth of x. Okay. Let's put that in. 1 minus 1 minus 2 cos squared x plus cos to the fourth of x all times cos to the 1/2 of x sine x dx. Yikey dikeys. What are we going to do with that? Okay, breathe. Look where we are. We're actually in a really good place. We're in a place where we can do a u substitution here for cos x, and we get sine x dx out, which means all we have to do is clean this all up so that it's integratable. And remember, up here, that's this part, right? That's where you just did all the distributions to put it together and then separated it into separate integrals. So let's do that. Easy enough. So if I put, well, in this case, I can distribute cos to the 1/2 of x times sine x in across my 3 terms of my first part of the integral. Eesh, that was badly said. So let's see. I'm going to distribute all of this to 1, which means I just have cos to the 1/2 x sine x dx minus, now let's review real quick. I took all of this and I distributed it to the 1. Now I want to distribute all of this to the second term, which is minus 2 cos squared of x. Well, the minus 2 part is easy because I know I can pull the constant out in front. That's just one of the rules of integration. And I'm going to multiply cos squared of x times cos 1/2, which is just the cos of 5/2 x, and I'm left with the sine x dx. Okay, I'm almost done. This time I want to take all of this and multiply it into the last term. So we have a plus, no constant to deal with, cos to the fourth of x times cos 1/2 is cos 9/2, 9/2 x times sine x dx. So now you can see that we're really set up well for a u substitution. But before I do that, let's talk about what we did. We noticed that the pattern fits the odd power, in this case on sine x, which means I'm automatically going to substitute 1 minus cos squared of x, right? That means I have to separate one of the factors of sine x out, which is exactly what I'm going to use for my u substitution. That's the setup here. So when I pulled a factor out of sine to the fifth of x, I just set it up back here with my sine x dx. Then make my substitution. It's not always going to be pretty. In this case, it was sine to the fourth, so I had to change to a binomial raised to a power. No big deal. I did my scratch work over here to show you what I did. I used a little substitution to show that it was really just the distribution of a binomial, and then made my substitution back into my formula. So 1 minus cos squared of x squared equals 1 minus 2 cos squared x plus cos to the fourth of x. Okay? Then distribution, distribution, distribution. That's just to get 3 separate terms that I can integrate individually using u substitution. Let's do that. So I'm going to let u equal cos of x. That means du equals, okay, so derivative, that means this is minus sine x dx. So my sine x dx is what I want to substitute, but this is a minus sine x dx, no big deal. Minus du equals sine x dx. That means I have a minus 1 included with my du. So when I rewrite this, I have the integral. Well, the minus 1 for this is going to come out front. So I have the opposite of u to the 1/2 du. Sorry, let me think that through, make sure. Yep. And then the opposite is going to be plus 2 times u to the 5/2 du. And then the opposite here is going to be minus the integral u to the 9/2 du. Let's integrate these real quick. I have minus u to the 1/2 is u to the 1/2 plus 1 is 3/2 divided by 3/2 plus 2 times u to the 5/2 plus 1 is 7/2 over 2, oops, sorry, taking the reciprocal, over 7/2 minus u to the 9/2 plus 1 is 11/2 over 11/2, and then plus c because I've taken the integral. Okay, now I've got to clean it all up and put my cosines back in. I think I'll clean it all up first and then I'll put in the cosines. So this is minus the reciprocal of the denominator, 2/3 u to the 3/2 plus 2 times 7/2. Well, that's 2 times the reciprocal, 2/7, 4/7 u to the 7/2 minus 2/11 u to the 11/2 plus c. So let me double check against my notes real quick, make sure I haven't made a simple calculation error. Looks good to me. So now I'm just going to put my coses back in. So that's negative 2 cos 3/2 x over 3 plus 4 cos 7/2 x over 7 minus 2 cos 11/2 x over 11 plus c. Now, I like to write my numerator and my denominator separately. You certainly could have just substituted keeping the fraction out front. Either way is fine. It's all the same and just personal preference. All right, so that's enough for today. We'll pick up tomorrow with examples of this second form of odd and even functions.